Yeah. Uh, so I'll do a quick brief recap of the stuff we did in last class. Essentially, we started off by talking about what the origin of this graph theory is. There was this town in Königsberg where there were these bridges, and people wanted to figure out whether there was some route which you could take so that you cross every bridge exactly once. So uh, in some sense you want to not repeat any bridge but cross every bridge and come back. Okay, you don't even need to come back, but after some point Euler proved that this is not actually possible, and he gave rise to an entire field called graph theory, because essentially what he did is there were these land masses connected by sea, and then there were these bridges, and he thought of each of these as vertices and these bridges as edges. So he converted that thing into a sort of graph structure where there are these points, and some pairs of them are connected with edges, while some pairs of them are not. And at the end of it, he all he had to prove is what is now called an Eulerian trail did not exist in this. Um, an Eulerian trail is basically where you want to cover every edge and in a path, but not repeat any edge. And so the essence of graph theory is these two terms, vertices and edges. And some pairs of these vertices will be connected with edges. Some pairs may not be connected. It's completely up to you. You could have an empty graph which has no edges. You could also have a graph which has everything connected to everything else. Um, Essentially, what makes graph theory so powerful is that it's a very abstract structure, right? All I've defined is some points and some edges which are joining each other. So I can really use this for a billion different things, and that makes graph theory one of the most active fields of research today. For example, graph theory is being used in AI. It's being used for computer data structures, for DNA tracing, and completely irrelevant and random stuff which you will think, okay, that's impossible. But somehow there is use of graph theory everywhere. And that makes it a really important subject to know about, whether you are doing math Olympiads or whether you're in computer science, or even if you're not. Um, but okay, a little more on the theory. So we spoke about these vertices and some edges, which some of them are joined by. And we also define a related term called degree. And degree of each vertex is defined as the number of edges which are connected to it. For example, this guy's degree is 3 because there are 3 edges which come out from it. And this guy's degree is only 1, and this guy's degree is 1, and this is also 1. Um, so that's simple enough, I guess. And then there is this term called path. So a path is similar to what we discussed earlier, which is an Eulerian trail. Except now, instead of not being able to repeat an edge, you cannot repeat a vertex or an edge. So just to make that more clear, for example, if I make a random graph, um, something of this sort is a path. Okay, just to make a few more edges, you need not have every edge in your path. So these could be some extra edges, but I can choose to have my path as only that thing. And I'm basically going from 1 to 2 to 3 to 4 to 5. And all of these are neighboring vertices. Neighboring essentially means that they're connected by edges. So 4 and 5 are neighboring, but 2 and 5 are not neighboring because they're not connected by an edge. Um, that is the essence of most terms. There's one final term which is called a cycle. Cycle is just like a path, except at the end you should come back to the original vertex. So, okay, not even that. You'll have to come back to 1 over here. So, um, a cycle is basically like a closed figure, like like you see in polygons and stuff too. But the interesting thing about graph theory is that the uh, the shape of the structure really doesn't matter to you unless you're doing some planar graphs or something. But because making the 1 5 edge as this big U, or making it like this, or making it through everything else, it means the same thing. It means that 1 and 5 are connected. So, and okay, as one final thing, there is also something called a tree. A tree is basically a graph which is minimally connected, which is to say that from any vertex, I can reach any other vertex using a path, except there is no cycle in it. So, for example, okay, it's called a tree because it looks kind of like a tree, right? These are like branches, and okay, you need not have only two branches, you can have as many as you want. Um, but it's something of this sort where there's exactly one way to go from this guy to, let's say, this guy, or from here to here. And you will never find something like this, which is a cycle over here, because you can go from here to here to here and back. So, what makes trees really so powerful is that if you remove anything from this, it suddenly loses all of its structure. So it's very strongly connected, so that it really allows this power of induction. Because, for example, if I delete this random edge, this edge, I've basically split this into two trees, one tree here and one tree here. And that really allows me to induct a lot of times. And those are some of the basic things we did last time. I won't go into too much depth. If you want to know more about trees, you can either go through some handout, or even the recording, I think, was posted. So we'll start off with this classes things. Um, Nothing too advanced. First thing we'll be defining is something called a bipartite graph. Does anyone know what a bipartite graph is? Come on, people, speak up.
It has no odd cycles.
Uh, a better definition, maybe. Not the one which I will use as a lemma
It
or
has
something.
few components.
Okay. So I basically, a bipartite graph is a graph where I have these normal vertices, except I've split these vertices into two parts. And the interesting thing is that within this part, this yellow part, there will be no edge. So I cannot have an edge like this. Same way, I cannot have an edge like this, but I can have edges like this. And the same way, I can't have an edge like this. So this is not allowed, and this is not allowed. So only edges are allowed from one component to the other component. So you can go like this, but these edges inside are not allowed. So why are we learning about bipartite graphs? It seems like a pretty random concept. Essentially, there are a lot of different things which can be converted into bipartite graphs. For example, something that I discussed in the last class too. If you have an n by m grid, um, something of this sort, and I choose to say shade some of the cells in this grid with yellow. Okay, this is very thick. Let me reduce the. Okay, something of this sort. So some edges are colored, and essentially I've chosen some, let's say, 5 out of all of those vertices. And what I can do is I can convert this into a bipartite graph, and that's really kind of weird, because what I'll essentially do is I'll make one set of rows and one set of columns, and each vertex represents a row. So this is the first row, second row, third row, and up to the nth row, and then m column, something like that. And now I join 1 and 2 here if 1 comma 2 is the one I had selected, something of that sort. So I'll end up with some bipartite graph, something like this. And notice that I'll never try to join something like this, because that's irrelevant to me, right? Why will I join row 1 and row 2? That's not what we're trying to achieve. So bipartite graphs, more than a restriction that you cannot have these edges, is an advantage. That uh, it makes the structure very easy to understand and to figure out. And okay, there are a lot of other places. This is a very random example where bipartite graphs gets used. Something of okay, an interesting thing is there are a lot of these questions in Olympiads where there is a magician and he has an assistant.
Oh yes,
Uh,
those
and what
election problems.
Yeah, and those are very interesting. Those are one of my favorite type of problems. I think Atul took a class on magician problems. I really
Yes,
like that.
yes.
Yeah.
He taught us magic, and
Yeah.
since then,
But okay, so a lot of those kind of problems, what you want to do is, assistant is basically going to give you something like 1, 2, 3, 4, and you need to guess that last letter, right? And that last letter could be something between 1, 2, 3, 4, 5. Let's see. I'm giving a random example. It's not really the best example, but essentially I can think of 1, 2, 3, 4 as the vertex on the left side, which is what the assistant gives. And the magician has to guess which one it is out of 1, 2, 3, 4, 1, 1, 2, 3, 4, 2, 1, 2, 3, 4, 3,
Halls
1, 2, 3, 4.
helps a lot in such
Exactly.
problems.
So Hall's theorem is something which is defined exactly for this, for something which is called a perfect matching. We won't get into perfect matchings today because I I was actually wondering whether I should spend this entire class just on Halls because that's something which is really fun. But
Like Halls
uh,
is worth another class.
yeah,
Also
exactly.
take another class.
Yeah, it's worth its own individual class, and I felt like we're doing intro to GT, so let's just do some GT stuff. Um, okay, so oh yeah, just okay, fine. I'll not call him assistant. I'll call him detective. Be happy. Um, but okay, the basic idea. No, wait, is the detective supposed to be the one on the left or the right? Uh, I don't know. It
Detective is
could be.
supposed to be on the right because he gives like consecutive cards thing from inbox.
Oh yeah. Okay. Um. Okay. Anyway, leaving all of that. So this is just a general idea of why bipartite graphs can get used. So what I was trying to make clear here is that you have all of these edges where each thing means a certain set of things. And what you want to do is you want to find some matching here, which is basically connect each guy from the left side to one guy from the right side so that the magician knows that if he gets this vertex, he wants to know this answer, this vertex, this answer. And that's what Hall's theorem is all about. If you are interested in that, I
But
think Pranjal has taken.
imagine using Halls for such a large bipartite graph in real life. Like you are
Yeah,
just
a lot
manually
of these things are
counting.
not practical,
Yes,
exactly.
yes, yes.
Yeah, but theoretically you can do it, right? If Halls allows you. Anyway, so the main lemma, which we'll be proving about bipartite graphs as we come back, and Atul stated it as the definition of them itself, which is good, is that a graph is bipartite if and only if it has no odd cycles. Okay, so first of all, what is an odd cycle? We spoke about cycles being paths in graphs where you have to come back to the same place. So you're essentially going from here to here to here to here to here to here. And a cycle is odd if there are an odd number of edges in it. So for example, here there is 1, 2, 3, 4. Wait, what have I done? Oh, 4, 5, 6. Yeah, so there's 6 edges, and so it's an even cycle. On the other hand, if I draw something like mm, this, there's 1, 2, 3, 4, 5 edges here. So it's an odd cycle. Essentially, you want to prove that a graph can only be bipartite if it has no odd cycles. And that seems like a very random thing, right? Like,
Like you can
how
just
is
try to separate things. Like if some like every vertex is having like an even cycle or no cycle. So take that even cycle. Like in the first step, you go to another thing and take that second thing to be
okay,
in the
wait,
second
wait, wait.
component and
Yeah,
such
I get
ways.
your idea, and
It is an
yeah, that's
algorithmic idea. Not a very
Exactly.
complete type. Yeah.
Yeah, yeah. But just to get a little more intuition on why this should happen, uh, what we defined when we were doing bipartite graphs is that a graph is bipartite if we can, if that what, okay, basically you don't want any edge to exist like this, right? And
If it has an odd
edges.
cycle, then you
Hmm.
can divide it up basically. Uh, when you have two connected, one goes
In
in
a,
set one, the other
excuse
goes in
me.
set two. And you repeat, and the last one, since it's odd, you'll have two connected in the same set. So this can't happen.
Perfect.
So
Exactly.
bipartite doesn't have a
Yes. And that's the easier part of it to prove that if it does have an odd cycle, then there is no possible way for it to be bipartite. Basically, just to repeat that, he said that let's say we start by putting this guy in, let's say we label these as one and two, the components. Can't call them components, but okay, the components of a bipartite graph, I guess it's legal to say that. So you put this in one, so this is forced to be in two because you can't put one and one together. So this is supposed to be one, this is supposed to be two, it's supposed to be one, and then you have one and one in the same. So that's the problem which comes when you have an odd cycle, that no matter what you do, if you had labeled this two, then you would end up with one, two, one, two. So these two would again end up in the same place. So that's why even cycles are okay, because in an even cycle, you'll have one, two, one, two, one, two, and there's no real contradiction. But suddenly, as soon as you have an odd cycle, there's a problem. The harder part of the question is that if you do not have an odd cycle, can you prove that the graph is bipartite? And okay, Anurag gave us a pretty solid idea for this, but let's get into a bit of what exactly the intuition is. Um, Essentially, that if you can label something as a bipartite graph, a lot of stuff is forced, right? If you just start by defining a random vertex is part one, then that literally forces everything this is connected to, right? All of these will have to be in two. And then everything each of these is connected to is in one. And this is connected to will come back in two. And this is in one. And then the next thing is in two. And then you could have some cycles as stuff as well. The only thing you want to prove is you will never end up with a place where you have already labeled this guy as two. You just label this guy as two, and now you want to relabel this guy as one.
You
That's a
can't
problem.
like because it will cause an odd cycle.
Okay, yes, that is true. Why exactly does that happen?
Like say you're connected some one to other twos. Okay.
One to other tools. Okay,
Like
let's.
some consider some vertex and vertex and it is connected to some k other vertex and vertices. Okay.
Okay, sure.
Now we know that for the sake of contradiction, assume that there is like two vertices in those k vertices such that they are joined. If there is one, if there is one such edge, then we make an odd cycle. We can just go like 1, 2, 2, 1.
Yep, yep. Okay, that's correct. A little bit of a more book approach of putting that, where what they basically do is they essentially say you start by labeling a random vertex as one, and now what you do is you take any random path. Let's say you want to figure out some random vertex which may not be connected to one. You want to figure out whether you should put this as one or two, right? Independent of everything else. So what you do is, if one and v are not connected, meaning there is no way to reach v from one, then it's basically irrelevant, right? Because one and v being in the same place or not being in the same place is uh, quite arbitrary, because essentially this is something we discussed in the last class as well. There are these things called connected components. Um, and within each connected component, you can get from that place to any other place in the connected component with a path. That makes sense, right? Like any place inside these, if I have a path from this to this, I'll call this is also a part of my connected component. But as soon as from one I cannot reach V, that means I cannot reach V from any of these points. Because otherwise I would be able to reach them from one, because one is connected to those points. So there could be other points here, and this could form its own connected component. So the basic idea is that you can solve the question independently for each connected component and then join them up. Joining them up will not make any issue because those different things are really independent of each other. Uh, okay, coming back, we saw that we have labeled the first vertex as 1, and we want to figure out some random vertex. Should we label it as 1 or 2? So what we do is we take a random path from 1 to V. Okay, that doesn't look like a path. But this is some path. And let's say the path is of even length. That means that the after the first vertex in the path, you went to 2, then you went to 1, then you went to 2, 1. And now that basically fixes it, right? That this has to be 2. Or if it was of an opposite length, then opposite parity length, then you would label it as 1. And now the thing is, if at the same time you had some other path which is saying, okay, no, I want to be 1 from this path and 2 from this
You
path.
have an even number of edges and you have an odd number of edges, so it forms a knot cycle.
Exactly. So this part will have an odd number of edges and this part will have an even. So the total thing will make up for an odd cycle. And that's not possible, right? Because we assume that there is no odd cycle. So
Yes.
that really proves the if and only if condition. That's actually a really strong condition, that a graph is bipartite if and only if it has no odd cycles. And a very cool problem on a similar concept. Okay, maybe I've already spoiled half the problem by saying it's a similar concept, but uh, 1 second, I'll just get that problem. Okay. Oh no, sure. Wasted this page off. Yeah. Okay, I'll give you all 5 minutes, and after that we'll discuss this problem. Okay, wait, there is still time left, but anyone with any ideas till now? Any interesting things they have noticed?
You can make a
Any ideas?
bit
Hmm.
global approach.
Global approach. Okay, interesting. So, what do you plan to do with the global approach?
But wait, I, I would really like to disclose it when I complete it.
Okay, okay, sure. Anyone else with any? Has everyone understood the problem? Should I give like a quick explanation? Basically, there is you start off with the complete graph, which basically means everything is connected to everything else. Um, so just for 5 vertices, I'll draw the thing. Did I miss something? No, I don't think so. Okay. So essentially what I'm going to do is I'm going to choose any cycle of length 4 in this, which is something like this. And now I can choose any random edge from the cycle. Let's say I choose this one and then I delete it, right? So my graph no longer has that edge. Now I can choose a different cycle. So let's say I choose this one. And again, I can remove an arbitrary edge. So let's say now I remove this. And the question is that I can keep trying to do this, but at some point there will be no cycle of length 4 left. So what is the minimum number of edges that we can reach while keep while we can only apply this operation?
Wait, no, I had to ask something. Does the graph remains connected even after any operation? I think it isn't. Or is it?
Good question. So the question is if you have a cycle of length 4, and now if I delete one edge, okay, wow, one
Mm.
second. Right. This is imagine it's connected, and I delete this edge. And the question is the graph still connected?
No. Wait, yes, it is.
Okay, anyone can explain why it is or it isn't, other than Anurag?
Okay.
Because deleting the edge doesn't disconnect anything because you can reach anything in the cycle through anything else, just along the cycle.
Yeah, it's like basically if there was some path which involved that edge, and now because that edge is gone, so like if this edge was really the only way to reach from one vertex to another vertex, now I can just take this path, big deal. So I've really not created any disconnection in the graph. If I had a certain way to go from one place to another earlier, I should still have a way.
So the minimum would
And
be like at most n-1.
correct. So we
Because
spoke
like
earlier about
at minimum it can be a tree. It can't go below a tree.
yeah. So we spoke earlier about trees, and essentially trees we spoke as our minimally connected graphs. Oh, okay.
And I guess for a tree construction we can give like no.
Okay, okay. But once we reach this, okay, minimally connected in the sense there is no cycle in this anymore. So forget 4 cycle, there is no cycle in this. So at most the answer can be n-1. It can't be less than sorry, n-1. It can't be n-2 or something because then the graph is just not even a tree. Means that with n-2 edges, I can't even make sure that the whole graph is connected. And as we saw, the graph will always be connected because at the start it's connected and after every process it's connected. But the problem is this is wrong. N-1 is not the answer.
Yes.
And
You can do n.
yeah, that is good.
Isn't it to n
No,
minus
you
3?
can construct for n. I don't know how to prove that you need.
Yes. N is equal to 4.
Okay, interesting. So first of all, just to get a basic idea on why n-1 doesn't work, the first thing you should try when you have such a conjecture
Like a
is
K3 remains. If you just remove it, a K3 remains. Then K3 is a cycle.
It's fine.
Wait, your voice is breaking. Can you just repeat what you said?
what is false? Yeah, I should draw these edges like one at a time so that they erase one at a time. Maybe there is some way to like
No, here it is
oh
like
yeah,
n
there's
plus 1.
partial
Yes.
erasing. Okay, yeah, that's what I need. Okay. But okay, so the first thing you should try when you have this kind of conjecture that the answer seems to be n-1. First thing I will try is I'll take a very small graph, like not 3 because then there is no there's no, okay, even 3 actually, because the answer for
But n
3
is
according
greater
to our
than equal to
claim,
4. It is like
is that
given in.
written?
Yes. N
Okay,
is
it's
greater than
given.
equal.
Fine, fine. Fair enough. But okay, so for a K4, which is a complete graph on 4 vertices, what happens is you, let's say, start with the main cycle, main 4 cycle. There are only 2 4 cycles here. One is this one, and then one is this one. If you can make out the colors, wait, let me use a different color. Something like this. So these are, or am I missing something?
You need
Uh,
to delete one edge, not like 2.
okay, wait, no, there are also other things. Yeah, you're right. Only one. Yeah, there's something like, okay, no, that's the same thing. No, it's a different
Like
thing.
one, it will be something like two right triangles on one base. It will be something
Yeah.
like that. Yes.
Okay,
But
but
we
okay,
have like
point is
5.
let's start by deleting some random one. The thing is basically symmetric, so it doesn't matter what you delete at the start.
Yes. Yes.
Uh
Exactly.
so okay, small eraser, yes. Finally figured this out. Okay, so you delete this one from that cycle. And now the only cycle that I can see of length 4 is this one. Is there anything else? No.
You can delete 1, 4.
Yeah, okay. But the point is whatever I delete now, uh like let's say I delete this one, I can't delete anything anymore because there is no 4 cycle left and I'm left with 4 edges.
This is the construction for n. So we are done.
It's not the construction. This is just an example. You'll have to
Like,
generalize the construction if you
It
okay.
ask.
does work. If you have another vertex, like induct, you can get this kind
Okay,
of
okay.
triangle.
Yeah.
Yes, we can end that.
Fair enough. But now the important question is why are we not reaching n-1? What is the problem? And the first thing that by
Maybe
psychology,
cycles of smaller lengths remain.
Like just prove
Like
that
length
one.
3 cycles still remain.
yes, very good. Length 3 cycles can be broken, first of all, because something which was a 3 cycle here is still there, is sorry, suddenly gone now. But thing is that because we're talking about all of this in bipartite graphs, something that should strike to you is that odd cycles, come on. What did we do? Did we delete any odd cycle at all? Yeah, we did. But the only time we could have no odd cycles is what we want to consider. Okay, this color is definitely not matching. But basically what I'm trying to say is, let's say after I deleted some edge of a 4 cycle, suddenly, magically, I managed to make this graph uh, bipartite, right? At the start, it's non-bipartite because at the start there are all sorts of fives. There is a 3 cycle, there's a 5 cycle, maybe 7, 9 cycles as well, and there are lots of odd cycles. So at the start, it's definitely non-bipartite.
But like
The
in
question,
bipartite, we won't have some kind of. No. Okay. Yes, you're right.
so basically, like if you reached a tree is bipartite because there is no cycle in a tree,
Yes,
right?
correct.
So you have no odd cycle. So essentially, if you can prove that the graph is never bipartite, then n-1 is rejected. And then you use what Atul said. You kind of try to induct that we'll come to, and then you prove that you can reach n edges in a non-bipartite graph. So like this graph is non-bipartite because there is a triangle here. and it has 4 edges. But okay, coming back to the bipartite part, essentially, let's say when I had this 4 cycle, it wasn't bipartite, but suddenly now it is bipartite. Can anyone tell me what the problem is?
The thing is, like, you need to have like another, like, say you have two
There are
components.
no 3 odd cycles anymore.
Sorry?
There are no 3 odd cycles anymore.
No, this is just only a part of the graph. There is more stuff in the graph. For example, I could have something like this, right? Something of this sort. And
Yes.
the thing is, I'm asking, when I erase this one, why is it okay? Here it's obvious that I still have a 5 cycle left, but in general, why is it again in the same way necessary that the graph will still be non-bipartite?
Like for it to happen, you need to like, for any cycle of 4, you need to like remove some k4 minus 2 edges. So in another ways, you need to find like k4 minus 2 cycles of length 4 in that. No, this is
Mm,
this goes global
You
really
can
quick.
divide your graphs into 2 sets, set 1, set 2, such that if
okay.
after deletion the graph becomes bipartite, that means you deleted an edge between 2 elements in the same set.
Uh, just repeat that. I think that's the right idea, but just go over that again.
You divide your graph into 2 sets, set 1 and set 2.
Before or after the operation?
Before.
Okay. So right now I have this edge with me, and I split it into 2 parts, but it's non-bipartite. So how can I split
Yes,
it into 2
but if it
parts?
becomes bipartite,
Huh.
like
Now
you
I can split it into 2
suppose that
parts,
it's
sure.
not. So, okay, so you suppose that it's not bipartite and that after a deletion it becomes bipartite. Then you
Correct.
draw the 2 sets after the deletion. That means
Yeah.
that before the deletion, there was a link between the 2 sets, between 2 elements in the same set,
Correct.
because it wasn't
Exactly.
bipartite.
Exactly. But
Then
now we're
since it's
seeing
a
that
4 cycle,
these two would have
there is
anyway
one
been
in
a
the
part of.
other 2 sets. Yes.
Yeah. Okay. So what he's basically saying is that after we deleted this edge from the 4 cycle, let's say this was a part of, let's say now the graph is bipartite, and this is part of group 1. So this is part of group 2. This is part of group 1. So this is part of group 2. But that means that these were anyway a part of different sets. So it was completely irrelevant, right? Another way of thinking about it is, um, let's say there was some odd cycle in our graph, not a triangle necessarily, but some odd cycle. And now we have essentially deleted one edge of this odd cycle to make the graph bipartite. So let's say this edge is gone. But we also know that this edge was a part of some 4 cycle, right? It could be any 4 cycle. It could also be something like this 4 cycle. I don't know. But we know that it was some 4 cycle. Okay. Uh, okay, there are some cases here, so I think this is a much neater proof. But what I was thinking of is basically that you still have an odd cycle left because uh, you've added 2 vertices to your cycle and it's still a thing. But if the things are inside, it's a bit of a problem. Uh, I
It's
mean,
like
okay,
after
even
the
that's not
process, you won't get like in his, we can already find such 4 cycles always until there are no cycles. But in always in such case, it would be like really complicated to find such things. You can just have like
yeah,
another thing was before only deleted. It doesn't exist now.
correct. So, okay, so this is actually a really good proof and very simple too. So you start with labeling one of that 4 cycle thing 1, label the next thing 2, label the next thing 1. You'll have to label this 2. All of these moves are forced. But that means that these were part of different things, and so it's irrelevant. So that proves our claim that the graph is never bipartite. And what does that mean? The graph can never become a tree because a tree by definition is bipartite because it has no cycles, forget odd cycles. So the best you could have reached is n. And what remains to show is that there is a non-bipartite graph with n edges, which can be reached. And that is basically a process of induction, and I'll not go over that. Maybe you can think of that as a thing to think about later. Um, so yeah, this was a cool question on how bipartite graphs can be very useful. And much more than that, I think the most important thing in this question is not getting carried away with this tree idea. So it's very important to try out these small examples. For example, trying out this n equal 4 here and realizing that you cannot reach the tree. You really think that uh, deleting cycles will end up with a tree, but if the question was that easy, then life would be very nice. So, and essentially, that even could inspire the bipartite idea, because one is that they're deleting 4 cycles, right? 4 cycles makes it, if you've done enough graph theory, the first thing that should come to your mind with an even cycle is odd cycles and bipartite graphs. So that's a very common thing to, okay, not very common, but a clear representation of something where it might be useful to think about bipartite graphs. Anyway, so we're going to try to generalize one of the main ideas we've seen in bipartite graphs. What we saw is that essentially we take a random graph. And let's say this graph is, okay, it's not bipartite, still not bipartite. I want to make it more nice. Okay, I think we can do that. But okay, so basically this graph we can call it bipartite by actually splitting it into those 2 components, or we can just color the vertices, like we label them 1 and 2. Another thing we could do is color stuff. So we could color this yellow, we could
Are you
color
trying
this
to introduce
green, this
monochromatic
green.
numbers?
Monochromatic numbers. I'm talking chromatic numbers is what you mean. And
Okay.
yes, I'm trying to introduce chromatic numbers. Uh, Essentially here, what I'm trying to say is that you could color the graph with 2 colors so that any edge is between opposite colors, right? You will never have a green to green edge. You will never have a yellow to yellow edge. All the edges will either be green to yellow or yellow to green. But obviously, this isn't always possible. Like as soon as I made this, there's a problem. Green to green is now there. So what I'll do is, instead of just 2 colors, what if I'm okay with more colors? So I give this guy a third color, let's say blue. Now everything works out. So the question is that for a random graph, we want to figure out what is the minimum number of colors that are required for the same condition to be satisfied, that you will never have an
It
edge
would be
from,
like the minimum km that could be found in the graph, maximum km.
really. So for
Like the
example,
maximum complete graph you can find inside a graph. Is it really, or am I wrong at something?
no, so one part of it is definitely correct, that if I have a complete graph on 5 vertices, on let's say 4 vertices here, then I need at least 4 colors, because at any
Yes,
point
yes.
I can't do that. But even with that restriction, it is
Like
not
it is not
necessary.
if and only if condition, we can
Yes,
get a lower bound.
I'll give you an example for even bipartite itself. Let's say we just do this. This graph has no like K3, which is complete graph on 3 vertices, but still you can't color it with 2 colors. You still need 3 colors because it has an odd cycle.
Mhm. Due to
So
the
one,
bipartite condition.
yeah, so one part of it is definitely correct, that if I have all of these 5 vertices, everything joined, then I need at least 5 colors, because if I try to color 2 of these with the same color, I'm dead. But whether even that is enough is a different question. In fact, if this was an easy question to answer, you would like it would be a very different world, because it's actually very hard to figure out whether a graph is even colorable with 3 colors. So it's not like, obviously you can do it manually, but for a computer, there is no efficient algorithm to figure out whether you can use 3 colors to color a graph. And that's how hard and surprising this problem is. That it looks surprisingly simple, right? I just need to, like, I don't know, check 3 to the n combination, but 3 to the n is not efficient. I want something which is something like n to the 3 or something. That's okay. But the point I'm trying to make is that chromatic number is not something that is very easy to figure out. Like for chromatic number being 2, we got a very clear condition that it shouldn't have odd cycles. There is no clear condition on whether a graph will be colorable with 3 colors. All we can do is create lots of different bounds. For example, one bound we created definitely is that if it has a k5, then we need at least 5 colors. If it has a k n, we need at least 10 colors, right? Um, in general, there is one interesting uh, question which you can try to solve. That is basically, um, if you have a graph G such that the max degree, again, repeating what degree is the number of edges which a certain vertex is connected to. Graph G such that the max degree across all vertices is delta. So prove that what we need to prove is that the chromatic number, which is, I'm not very sure on what is the right way to draw this, but I think it's drawn like this. Chromatic number G
At least
is
delta plus one. At most.
exactly. It's at most actually. No, is it at least at most? What am I doing? Uh, yeah, it's at most delta plus one, right? At least delta plus one is dumb. That's just wrong, because I can just take some graph like this, and this I can color with 2 colors, but max degree is some very high number. Okay, so try this out. This is a cool question, and it teaches us a cool concept. So it's actually used very commonly in, not in graph theory, but somewhere else. I won't spoil what that somewhere else where else is just yet. But think about it for, let's say, another minute or two, and then we'll talk. Okay. Um, anyone with any ideas?
I think I have an idea. You
Yeah.
take your graph
Mm-hmm.
and then you start with the vertices,
Okay.
and it's like an algorithm. The idea is
Yep.
that you color it, and so if there is no problem, then it's okay. If there is a problem, that means that it's the same color as one of the adjacent vertices. In this case,
Correct.
since the max degree is delta, and you have delta plus one color, you know that you can fix it by changing the color of the one you just colored.
Okay. But what if that creates another problem?
This counts because you have at most delta colors taken, because the degree is at most delta. So you at least have one color that is free.
Um, 1 second. So basically, we're saying that, let's say there was one guy, let's say we tried to color the people, and we followed this method of giving different colors to different people. And as soon as we reach this sort of problem where two people are with the same color, then what we do is we realize that, okay, this guy has only at most delta plus one delta neighbors. So there is still some guy who, like, there is, even with those delta neighbors, they could have accumulated at most delta plus delta colors. And still there's a delta plus one color which is left. So I can change this to that delta plus one color. And now we have one problem less to solve. We've not created any new problems, right?
Yes, it does not create any new problem because you're coloring vertice by vertice, and the idea is that you fix the problem whenever you've colored the vertice. That you
Correct.
can't like go back to a vertice you've just fixed.
Yeah. That's a good way of thinking about it. Anyone with any other ideas?
I guess I have another
Mhm.
idea. Okay. Like every vertex at max has a degree delta. So
Okay.
the upper bound can be touched when you can get an k delta plus one in the graph. Okay.
Sorry?
The upper bound can be touched if
No.
I'm
Oh,
giving
wait,
an
what's this?
construction, bro. I'm giving
See, K
construction.
delta. Okay, fine. But see,
Okay.
I'm not saying graph G has delta vertices, by the way. Graph
I
G can
know, I
have
know.
1,000 vertices
No,
also.
I know.
Yeah.
But I'm
Go
trying
ahead,
to
go
give
ahead.
an construction. Okay.
Okay.
So like if you have some color, if the monochromatic number is greater than equal to delta plus 2,
Okay.
okay, so we either have a k delta plus 2 or we have some condition, some pigeonhole condition such that some one vertex is connected to delta colors. It has like some two colors equal to each other.
I don't quite get you. Like, pigeonhole condition. What's the pigeonhole condition for bipartite graphs? I don't understand.
No,
Like, if
no,
you have
right.
a five
Okay.
cycle,
Mhm.
what is the,
Like
like,
you said, you can't color it in two parts. Okay. You
okay,
can't color it in two colors. But in that
sure.
condition, we had a pigeonhole condition because like consider any three vertices. If we color it from two vertices, then two of them are colored the same, and eventually we get some two neighboring vertices which have the same color, right?
Sorry, I didn't get the last part.
Okay. So like consider in this pentagon thing, just like
Hmm.
try to use the pigeonhole to prove
Okay.
that there are at least, if you try to color it by two colors, there are at least like two neighbors which are of the same color.
Not very easy to conclude in general, right?
Hmm.
Like, if you have three people, now how much will you go around saying that, okay, one and two, two and three, one and three, one, okay, this will anyway have to be by pigeonhole. I don't know. It doesn't seem very um, like a clear cut way,
Yes,
at
yes.
least at the very
Okay.
least.
Hmm.
Another idea which I have seen before, and okay, by the way, the first idea is the most intuitive one and probably the best one. That is basically you do whatever you want, and as soon as you have a problem, just realize that you can fix it, right? And you're not creating any new problems by fixing it. because you have that many colors at your disposal. Another way of a little more of a something called a greedy algorithmic approach here is that, or maybe not a greedy algorithmic, more like inductive approach, where let's say I have colored the first k vertices so that what we want is satisfied. Now I'm trying to color this k plus 1th vertex. Okay. Uh, Now I know that the max degree of all of these inside was at most delta. Like if in the entire graph it's delta, and inside that also it's at most delta. In fact, it'll probably be lesser because this guy will maybe add up to the max degree or something. I don't know. But it's at most delta. So this can be colored with delta plus 1 colors by induction. Like that's our inductive hypothesis. And now all we want to prove is when this new vertex comes in, we can color this also with one of those delta plus 1 colors.
The
And
thing
while
is, you
that,
can find like at least one vertex in that old graph that isn't connected to the k plus 1 vertex.
one vertex, that's also very weak. One vertex is not what we want. See, it's not like, no, this doesn't have delta vertices right now. This has random k vertices.
Mm-hmm.
So we know that this guy has at most delta neighbors inside, right?
Yes.
So at most delta colors are not allowed. Correct?
Yes.
Like if I am connected to 5 people before me and I can't be any of those colors, then fine, I'll just be the 6th color. So because there are delta people which I'm not allowed, but the number of colors is delta plus 1, I can just choose whatever is left. Big deal. And now I've basically created a k plus 1 ka group where everything is fine. Now a new guy tries to join in. And again, he has at most delta neighbors, so you can label him as well. And this is also sort of like a greedy approach because one at a time, I'm just adding people into this, not thinking about how this could affect what is happening in future, because like the condition is pretty weak, and that really allows me to play around a lot, and like basically doing anything should work in some sense. And that's exactly what we did earlier too. We essentially did anything, and if you had a problem, it's okay, we'll fix it, don't worry. So that works out well. Okay, maybe I shouldn't erase that. These are good things for notes. Um, okay. Anyway, um, so okay, so this is one of the most common problems on chromatic numbers, where this is a one of the good bounds. Matlab, obviously this has a lot of generalizations,
Are
but
you trying
is
to give that
bounds.
crazy physicist problem that you gave me?
I do have that on my list. If you think that's worth giving, maybe I can give that.
Yes,
Uh,
that is.
okay, sure, actually, let's do that. But that's actually not a bad problem to do straight away right now. Let's see. Hmm. It's a bit long, okay? People don't get scared of it. If you want, I'll just explain it out rather than having to read that entire thing, because you'll probably get bored reading it halfway through. 1 second, I'll just shift this. Uh, wait, I can do that. Okay, nice. Right. Uh, Essentially what this problem is, it's basically saying that, um, okay, let's just read through, even I do not remember this problem perfectly. A crazy physicist discovered a new kind of particle which he called an imine. Okay, I don't know what's the intended pronunciation. After some of them mysteriously appeared in his lab. Some pairs of imines in the lab can be entangled, and each imine can participate in many entanglement relations. The physicist has found a way to perform the following two kinds of operations, one operation at a time. If some imine is entangled with an odd number of other imines in the lab, then physicist can destroy it. At any point, he may double the whole family by creating a copy of each imine. During this procedure, the two copies I dash and j dash. Okay, okay. So essentially, what you're saying is that one step is basically if the degree of a certain vertex. Acha, okay. First of all, we're starting by calling these imins basically are vertices. And then there are these entanglement relations, which basically means an edge for us, right? So if two imins are entangled, we join them by an edge. If they're not entangled, we don't join them by an edge. So something like this, we have our graph. And essentially anything which has odd degree, for example, this guy has degree 1. So you know that as soon as this is entangled with an odd number of other imins, which is degree odd, we can just delete it. So we can get rid of this guy once and for all. One person lesser to worry about. Problem is that at some point, maybe what will happen is everyone has even degree and you can't do this. So then for that case, there is this other operation where he may double the whole family of imins in the lab by creating a copy. So essentially, I'm going to take all of these. I'm going to copy it and I'll paste it. Okay. Yeah, let's pasting work on this. Come on. Yes. Okay. So we have, oh, you've created a copy of everything that was already there. And it's the exact same graph. So if 1 and 2 were, so if let's say I label the stuff for the sake of completeness, like 1, 2, 3, 4, and 5. Now this guy is also 1, 2, 3, 4. Oh, sorry, 4 and 5. And it's the exact same graph, except for the fact that now I will also join 1 and 1. I'll join 2 and 2. I'll join 3 and 3. I'll join 4 and 4. And I'll join 5 and 5. So in some sense, it's getting more entangled and you've doubled everything. So yeah, I and j become entangled if I dash and j dash are entangled, and vice versa. And I dash becomes entangled with its original I. Okay. And the question to prove is that the physicist may apply a sequence of these two operations, resulting in which in a family in which no two are entangled. So what will happen after this? You doubled everything is, so the problem is we were stuck, right? Everything had become even degree. Now when you doubled it, everything will suddenly have odd degree because this guy has increased its thing by 1. So now you're allowed to do a few unentanglements, but then you might get stuck again. So you want to show that, okay, I might get stuck again and then I might have to double again. But at the end of the day, I will be able to reach a place where nothing is entangled. So yeah, that's the problem. And if you want, I'll scroll back to the problem and think about it. It's a full problem. If you want, I can actually leave this for, like homework type problem because it's worth thinking about on your own. Plus, the main idea is already spoiled. Uh, and if it wasn't till now I have spoiled it. So what do people prefer? Do you want to do the problem right now, or do you prefer to try this out later?
Launch a poll because here people don't want to speak at all.
Okay. Uh, Fine. I'll actually launch a poll. I've never done that before. How do you do this?
You go to Zoom template.
Yeah, but I'm sharing. That's the problem. There are lesser options here.
No. Wait, I'm just saying. No.
Okay, but anyway, come on, people speak up. That's enough. Now I want the answers. No one can tell me. You prefer to do it, or you can tell on chat if you want. Oh, I think you need to like install that app on your thing. That's too much effort.
No, you don't.
No, like within Zoom, you need to install this app. let's
so
be.
you
I
are
think this
using
problem
Zoom and browser.
I will leave this for now.
Okay.
Maybe at the end of the class, if people want to discuss it, I'll
Leave
discuss
it
it.
for homework. I guess it
Yeah,
is worth for sure.
yeah. Also, my things got hanged. I'll have to restart sharing. It happens like halfway through the class for some reason.
Are you doing it on your iPad?
Yeah.
How do you like turn on video from this
No,
laptop?
this is computer, like laptop, computer, and give me
So
a
you are
minute.
sharing screen from the computer only. And you're turning video on from the computer only. How are you like then using the iPad?
Magic.
Yes. Something only Atul knows.
Oh no, oh yes, Atul knows. Wait, what's happening? Give me a minute. Okay, should work now. Yes. Uh, full screen. Now share. Yep. Okay. So we have two options now. There's not much time left. I was actually hoping to do a few maximal kind of ideas. Maybe I'll just run through a few of the ideas. We'll not do the problems on them. And I want to do one very cool problem, which Atul showed to me for the first time. Uh, I think Atul can even guess which problem it will be.
But Atul
Um,
isn't here, sadly.
oh wait, he's gone. Oh, that's sad. Okay, okay. Anyway, so first of all, some of a few ideas. There are so it's very useful in general with not just graph theory but combinatorics in general, and maybe even in number theory and stuff, where you take these maximal ideas, and the essence of it is essentially I say like in my graph G, in graph G, select the longest path. So what selecting the longest path does is now I have a lot of rigid structure, because essentially if there was any random vertex, first of all I know that it won't be connected to this guy, because if it was connected I could have made a longer path. And if I have something connected to this end, that's also not possible. And there are a lot of these kind of problems which will come up, and that really gives us a lot of structure to work with, because a lot of times the graphs are so general that we don't often know what is the best way to approach it, because like you will try to say that okay, this person should not be connected here, but then it should be, right? There's no condition on the graph until you create some sort of structure in it. Maybe it's a tree, maybe it's a cycle, maybe you're creating a bipartite graph. Some sort of structure is always necessary for you to do any sort of thing. Um, but okay, this was one idea. Take the longest path. Another similar idea is take the longest cycle. So this also works in a very similar way. Now, if I have a cycle, I know that if there was some random vertex just connected to this guy and this guy, I could have added it into the cycle. So that already gives me a lot of powerful structure, that there's no vertex which should be connected to two consecutive one of these. And these will all be a lot more easy to understand when you do problems, but we're running low on time. So maybe one problem I'll give, which you can try out, is Hamiltonian path. So just Google what a Hamiltonian path is later on. Prove that in a tournament. These are two words you'll have to Google: a tournament and a Hamiltonian path. Tournament. There always exists a directed Hamiltonian path. And okay, so these were some of the basic things which you can do for maximal structures, but one other two which are really, really important, which you should know about, are two things called cliques and independent sets. Anyone here can tell me what each of these is?
Wait, what is in directed Hamiltonian path? Can you repeat this?
Basically a tournament is a KN, except every vertex has a direction. So you can only go from one side to the other. And directed Hamiltonian path means that you should be going in the direction of this thing, right? So it's like, everything is joined. So obviously there will be a Hamiltonian path. Again,
What is in
Hamiltonian,
Hamiltonian path? By the way?
yeah, a Hamiltonian path is the path which goes through every vertex and does not repeat any vertex. Path in general does not repeat any vertex. But basically, if this graph wasn't directed, then you obviously have like anything as a Hamiltonian path. But otherwise, you have, when it starts getting directed, then you have these problems. And thinking about the longest path is something which is really important here. So that's the context to which
We
I have
can use
given this
an
problem.
maximal idea here, extremal idea.
Yes, exactly. The idea will be to use longest
Like say
path.
some two vertices don't have a directed Hamiltonian path. Okay.
Hmm.
Just note that we can just try to increase the number of points we go through that.
Sorry?
Then we can just try to like increase the number of points we go through in the path. Like say there was a
Yeah.
maximal path G.
Yeah.
Yes. Okay.
That's the main idea. Let's not get too much into it. Just let everyone try the problem. It's a cool problem to try.
Okay.
And not very hard to. It's something that's doable. But yeah, I don't want to rush through stuff also. It's better we just okay, let's just do clicks and independences because it's written it down. Can anyone tell me what each of these is?
Cliques are like some complete graph. Some part of the graph is complete, so it is a clique.
Yeah, exactly. So it's like you might have some random big graph and some small section of it has every edge connected, right? So like for this section, you have every edge connected. So this is in itself a complete graph on 4 vertices. And maybe this guy was also connected to all of these. So then we would have a complete graph 5 vertices. Similarly, independent sets is where nothing is connected within that component. So it's somewhat like a bipartite graph ka part where any
Like
part within the bipartite thing will
independent
never.
is mostly used in some operation kinds of thing. Like if you are doing operation on some connected or component, then it doesn't affect the another component, and you can just like try to index on the number of components.
Okay, that's one place where it could be used. But the more place where I'm coming from on these kind of problems is where you have certain very weird conditions. Like often you have these conditions like you have 4 vertices and you want to you know that out of them either 3 are all connected to each other or 3 are none connected. So those kind of things work very well with stuff like cliques and independent sets because I can say that anything outside, if I pair up with these 3 and I use that 4 condition, then I know that these 3 will form this thing, something like that. So I'm not giving a concrete example, but that's sort of the idea of taking maximal structures in these cliques and independent sets. I think we've covered a lot. The main takeaways, I guess, are that essentially to start with, graph theory is one of the most important things in general nowadays. Um, Not just for math Olympiads, but I think it is a really powerful thing and something all of us should know about at the very least. And we learned about trees and stuff, which I was not really learning, but a quick introduction. Bipartite graphs, that was interesting. We learned how different things could be represented by bipartite graphs and how something as random as magician and assistant problems could be converted into these kind of graph problems, which sounds really interesting. And that also reminds me of once I'd written this coding question where basically there's a 2x2 Rubik's Cube and you want to find the optimal way to solve it. So essentially what you can think is that uh, any position on this Rubik's Cube, like any coloring of the edge on the of the different things on the
Multipartite graph can we use it?
no, this is not really bipartite or multipartite. I'm just using a graph. And essentially, these are different, like for every different combination of colors on this on the different squares of the Rubik's Cube, I can define a vertex. And I'll join them if by moving like one thing up, I can get to the this thing. And then I basically want to find like the shortest path from a starting vertex to the final vertex. And that's a very common question in graph theory. It uses something called a breadth first search. Um, you can read about it if you want. It's actually really cool. And I think it was covered in one of the OMC lectures earlier. Not sure when. I think I don't remember. But and then we learned about how bipartite graphs won't have word cycles, which is really powerful because we realized that for if you have more than two colors, then it's suddenly very hard to comment on what makes it three colors or what doesn't make it three colors. But for two colors, we have this very strong condition of word cycles. And we solved this cool problem about remembering to check out your guesses and seeing whether they work. And we also saw how max degree in if max degree in a graph is delta, then the chromatic number is at most delta plus 1. This problem is really, really good. We have about 5-6 minutes. I guess I guess I'll not do
Leave
this
it, just
problem.
leave it.
Yeah. Anyway, Anurag, you have done this problem, right? Um, okay. So yeah, this is the other main idea, which I'm sorry I wasn't able to discuss too much in depth. But maybe in future, if I get to take another class, we could discuss more about this.
Or just share the recording that of Anant Mutgal's class.
Oh yeah, yes, that's
That is a
actually
really cool class.
yeah, that was one of my favorite classes. That's also one of the few classes I attended. But yeah, I love that class. Um, yeah, that's very good idea. And basically, he spent the entire lecture talking about maximal ideas and how you should come up with these kind of ideas because it seems very random in a solution when the first thing they say is consider the longest path. And that seems like, why would you think of that? And often there's a very good intuition behind thinking about such a thing. Or even if there isn't such an intuition, you should try to, especially when your thing is suggesting to think about something like a clique or an independent set, maybe try both of them. You won't know which one works. Maybe neither of them work, but it may just be worth trying out. So yeah, I guess that's mostly it. There's one super cool problem which I would like to give. I've already given two problems. I don't want to give too many. And obviously you can choose to do or not do the problem, but I think all of these problems are really cool. Um, I might also make a handout most probably in, I don't know, 2-3 days. I'll try to uh, post it on OMC and stuff. But here's the question. And the best part of this question is what really makes it so hard. The idea is that you would have no idea when you see this question that you need to use graph theory. And I've given you the biggest hint possible, which is that you have to use graph theory. And yeah, this is the question. I'll also send these notes, by the way. So yeah, this is one of Atul's favorite problems, I think. He always keeps bragging about this problem. Not always, but okay, that's strong term. But anyway, this is a good problem to try. If you want, you can take a screenshot of this and try it out, or
What
I'll
is the
anyway send these.
source, by the way?
Source, interesting question. It's actually a question in a competitive programming exam where you needed to not just
No
show that
problems.
there
I am
exists.
also really bad at remembering sources.
No, but that's the thing. This is that's I don't want to scare you with that, because there the question was you need to find that A1 to AI, which is like the subset which has some zero, which is much harder. But it's not much harder. It's once you get the math part of it, the computing part is just the coding. But getting the math part of it is what made it so hard for a lot of the people in those coding competitions, because they couldn't figure out the math behind it.
Do you remember the resource, or you just don't?
Yeah, it's a code forces question. I
Oh,
can send
okay.
you the link, but then
No problem. I don't use code forces at all.
okay. Also, it's I think in one of the Otis units, it's an IOI.
Oh,
Okay. Chalo.
but okay. Thank you.
Wait. I'll stop recording. Anyone has any questions about today's